Okay, I guess like we're live. So yeah, I was gonna stream like earlier, but I procrastinated for like 2 hours. So anyway, yeah, we're right. Okay, so yeah, we did a stream like 2 days ago, and we made a empirical discovery. Which I don't know. It's probably I mean, yeah. So, okay, so we'll just explain the empirical discovery, because yeah, we were then gonna try to see like if we could generalize it to higher dimensions. So what we're doing is we're generating linear threshold functions in degree input dimension 4 by like random search, I guess. And so each column, also these are balanced, meaning the bias is 0. Also meaning, like in each column, the number of purples is equal to the number of yellows. Yeah, so anyway, these are columns. Each column is a function. And yeah, we're interested in the like observation of like the first column is an input identity function, meaning if you list, so we're in 4 dimensions. So there's 2 power 4, 16 possible binary inputs. And if you list those, in the like lexicographical order, the leftmost column will be this column. But like interpreted as a function, it's just a function that returns x sub 0, like whatever. So it's an input identity function. I think they usually call them dictators in the literature. But that's a stupid name to me. So anyway, yeah. So there's kind of this observation that if you look at like what's going on in the first couple columns here, you start out with an input identity function, and then when you go to the next column, like you're like transposing 2 points. I don't know if you're transposing them, but yeah. And then you go to the next one, and then you have like 2 pairs of points. Yeah. And all of these pairs of points are negations. Like each pair is a negation pair. So anyway, this sort of kind of suggests the question. Maybe a linear threshold function, specifically with a 0 bias, has to be similar to an input identity function. And so we investigated that empirically. That's where the concept of similarity is given by correlation, like computing correlation. So specifically what we did was we each of these columns we dot product it with a linear threshold. So like we create this matrix where the columns are the input identity functions and the rows are all possible linear threshold functions, and then we're looking at the dot product. And yeah, so let's just run that. Ooh. Yeah, I was like doing some other stuff. I think we can get rid of all of this for now. And yeah, that should work. Righty, right. So yeah, okay, cool. So I guess this is I get my computer to work. Why? Okay, so yeah, so this is the yes, yeah, I think, I mean, the whole thing we were gonna do was like, I mean, it's not gonna work, but we're gonna stare at this matrix and see if we see any patterns. Wait, okay, like, let's interpret the matrix. So there are 14 rows, and that is because I am using the unique operator. So I'm actually going to look at it without the unique operator. Yeah. Right, okay, so like up here, we have what, like 104 possible linear threshold functions that are balanced for dimension 4. That's probably somewhere in like the Encyclopedia of Integer Sequences. I mean, you'd need more numbers, but anyway, right. So we have this matrix that we just produced, which is 104 rows, right? So for each LTF, and then 4 columns for each input identity function, and yeah, and then we have like color-coded correlations. Yeah, it might also be better to actually look at the number, like the actual numbers. Yeah. Wait, how did that compute if I... That's weird. Right. Okay, so we'll also get the numbers. And yeah, I mean, like, we're sorting the matrix. So, DIDXs. Oh no, yeah, I'm already printing that actually. Okay. Yeah. So yeah, I'm not okay. So anyway, yeah, okay. So it's like you know, there's like a couple functions up here that all have 0 correlation with the input identity. And what it's saying is that if you have 0 correlation with the x0 input identity function, you're probably one of the other input identity functions. But not necessarily, because you could be one of these guys that are light blue, which I think is, I'm going to say is 0.5. Yeah, I'm not sure why that is. Yeah, but I wanted to get the max. Vid stack D x's D x's. Great. And where did that go? Okay. Okay. Right. Okay. Yeah. So like this number, this light color is 1/2. So that means if you have zero correlation with x0, you either are one of the other input identities, and you have like perfect correlation with them, or you have half correlation with every other identity. So that's weird. Yeah, okay. Moving on. This correlation level is 0.25. So you can be 0.25 correlated with x0. And in which case, you will be 0.25 with every other input except for one. In which case you will be 0.75. I guess like you can almost kind of interpret that as like taking this function like, and then like taking some of the correlation here and then like spreading it over to the other input identity functions. I mean, that's like completely abstract, but also probably incoherent. So, alright, let's look at this block. This is like a light blue, and that would be 0.5. So this is 0.5 and 0. Okay, so this is kind of, yeah. You can be, okay, so it's saying you can also be half correlated with 3 of the functions, and then 0 correlated with one of the other functions. And this block would be kind of a continuation of this block, and this would be like a continuation of this. Like, this one is the identity function. Great. So mainly the like question we were interested in was if you yeah, like for each linear threshold function, like for each row, if you consider the largest correlation in that row, how small can you make that? So it's like a mini-max thing. And we can compute that right here. And so for n equals 4, we get 0.5. And but for larger n, it seemed to kind of I mean, based purely on this script, it seemed to like asymptote at 37.5, which is saying that the farthest that a linear threshold function can be from any input function is 37.5. Which is like equivalent to saying that if you take a random LTF, it has to agree with one of the inputs on 37.5% of the inputs. It has to agree with one of the input identity functions on 37.5%. And yeah. So first of all, we don't know if that's true. Second of all, I don't know how to, probably not going to be able to prove that or like generalize it. Just staring at plots. But I did do a thing where I think I have enough code where you can. So, okay, so we'll go to like a higher dimension. N equals 6. Yeah, I think basically we have enough code where you can where we actually like picked out what those functions look like that are maximally distant, and yeah, but anyway, so we'll look at that for n equals 6, and let me do this minimax compute. No, I have to compute d first. Okay, so we're gonna compute d. These are the input identity functions, which are just the columns of the inputs. Right. And yeah. Okay. And I think on this one I'm going to want to show the uniques only, because there's like way too many functions. So we're just going to show rows that are unique. So we're going to be dropping in some of the functions, and who knows what's going to happen. Right. Why am I getting 2 plots? Oh. Yeah, because I didn't, okay. Okay, so these are like unique. Yeah, I think the dimension here is too high. Right. So this is the same plot we were looking at for n equals 4. And I think it like somehow has the interpretation of like a decision tree. Although I don't know how to express that. There's gotta be like a decision tree in there somewhere. But, so, okay, so let's do that minimax computation. For n equals 6, you get 375. And then we can pick out those actual, we're going to pick out the rows where you get 375. And then we're going to show that. Yeah. And, okay. Right. Yeah, that's pretty cool. Yeah, so each of these columns, now there's some sampling error because I'm not sure I'm generating all possible LTFs. Anyway, like each column is a six-dimensional Boolean function, 64 inputs. You know, so there's like, so the rows correspond to each possible input, and the column corresponds to binary labeling of that input, and these all have the property that they are maximally distant from any input identity function. Yeah. So it looks very cool. But the question we were, no, wait, what is the question we're trying to ask? Yeah, we're trying to say, like, does that 37.5 or 0.375, whatever, does that hold for all n? I don't really, and yeah. I was hoping you could like stare at the functions and be like, yes, I see a property that you can generalize to higher dimensions. But I don't think that happened. Anyway, like it's a cool matrix. So, I mean, I'll think on it. Yeah, see what happens.